So today let's continue working on this bench power supply. It has 2 adjustable outputs and 3 non-adjustable outputs, and at this point everything seems to be working other than this non-adjustable output of 15 volts, which is meant to supply 1 amp, but no, it only supplies 15 volts with no load, and when I loaded just a couple tens of milliamps, the voltage drops to just a couple volts. It supplies just very little current, and I was previously trying to load it with a resistor and measured the voltage drop on it using an oscilloscope to make sure there is no oscillation, and there was just a pure DC voltage. And during the test I could smell a typical smell of a burning resistor or a resistor getting way too hot, and it was probably on this board. And I also identified that the main transistor, the main power transistor on the big heat sink for this power supply is the one at the bottom of this heat sink, and I was measuring the voltage between the emitter and base. I did it off camera, let's do it once more. The voltage base to emitter is just 85 millivolts. And this is definitely not going to turn the transistor on. And I was also trying to identify which resistor is getting bloody hot and smells, and it seems to be this resistor. Let's take a closer look at it. It's a bit darkened, and it's an 820 ohm resistor. And in the schematic it's this resistor. It goes from the emitter of this small transistor, and I traced this connection goes to the base of the main big transistor, and this connection goes to the emitter of the big main transistor. Let's draw a simplified schematic. The transistors are basically a Darlington pair, sort of. The base of the small one is driven by the chip. This one amplifies the current, and then the final one, and this goes to the output of the 15 volt section. And here of course the unregulated voltage goes in from the rectifier and smoothing. And this is the resistor which is getting bloody hot. And for it to get bloody hot it has to have a lot of voltage on it. But at the same time, the voltage measured on this transistor from base to emitter is super low. Just a quick check using the calculator. The resistor is rated for a quarter watt and it's 820 ohms. So the voltage on it has to be over 14 volts to exceed its power rating. How can you have over 14 volts on this resistor and yet about 80 millivolts on this junction when it's connected in parallel? So is this connector bad? Is it not making contact? These pins go into the connector at the bottom, and I started measuring. Okay, probing the first pin of the connector on one side and on the other side, and I get no connection. The very first pin of the connector is not making contact. And this is what goes to the base of this transistor, the main power one. I'm looking closely at this connector and there seems to be some damage in this first hole. And this definitely makes sense. When this power transistor is disconnected, then all the current tries to go through this resistor, and that's why it's overheating. It basically just goes through here and through this smaller transistor, and nothing goes through the big transistor. And also going through this resistance, the voltage drops to almost zero when loaded. And of course the overload lamp is never lighting up because the current through these current sensing resistors never exceeds 1 amp. I was thinking about disassembling the connector and trying to fix it, but it's actually not screwed together, it's riveted together. I could try to drill the rivets out and then replace them with screws, but I guess the entire connector would probably fall apart. So I could rather just jump it with a wire, but of course removing the board and working on it further will be a bit tricky. Or I noticed the connector has some unused pins, one here and one here, so I could just reroute this connection to, let's say, this pin. Okay, the wire from the pin 1 is now rerouted to the pin 14 of the socket, which was unused, and it's also jumpered to this one on the board. And I also noticed that the burning resistor, 820 ohms, might have been actually replaced already for a bad value, because in the other identical section, in the same position, there is a 220 ohm resistor instead of 820 ohms. I guess somebody was already trying to solve this problem and already once replaced this resistor, accidentally putting 820 instead of 220 ohms in it. In the other identical 15 volt section, the same resistor is 220 ohms and has no signs of a botch soldering. And this one for some reason is 820 ohms and it's botch soldered horribly. In this position it's not critical, but I guess it's meant to be 220 ohms. 820 is too much. I will probably put this 215 ohm resistor here, which is much closer to 220 ohms. Now this resistor is in way closer to what it should be. And now big testing time. Let's turn it on. And it actually seems to supply enough voltage for this tester, and 0.2 amps, 0.68, 1 amp, slightly over 1 amp. And then it trips and the lamp lights up. And also this meter seems to work. It trips slightly above 1 amp, and of course the threshold can be readjusted using this potentiometer. Now both 15 volt outputs are working well. Output A is working perfectly, but with output B I noticed one oddity. When it's fully loaded, it produces weird buzzing. Only output B does it, not output A. When loading output A, the one I fixed, I can hear just a very quiet buzzing of the transformer, what I call a healthy transformer buzz. Not sure you'll be able to hear it in the video. But when loading the output B, the buzzing is different. And this is not a healthy buzzing. Normally a transformer is buzzing at 100 Hz. And that's because the magnetic forces and the magnetostriction in the iron core doesn't care about the polarity of the current. And the same applies to a buzzing fluorescent inductor, AC electromagnets, solenoids, relay coils. But if you actually hear a 50 Hz buzzing, it means that there is some DC bias, some DC current superimposed on the AC current, or some imbalance between the half cycles. And there is more current in one half cycle than in the other. It sounds like a transformer loaded in just one half cycle, and it made me test the diodes in the bridge rectifier. One diode half a volt, another diode half a volt, this one again half a volt, and this one? What the hell? It's open circuit! Which is unusual because typically rectification diodes, when they fail, go short circuit. But this really explains the weird buzzing of the transformer. The only marking of these diodes is a blue band, and it seems like one was already replaced because it's soldered with a much longer pin. But I identified them as 1 amp 150 volt diodes. I don't have the blue diodes, but I have some violet diodes. And these are 1 amp 300 volts. Very similar but a higher voltage version. I have 7 pieces, I tested them, and 6 of them are good. And one of them is again open circuit. So it seems that these diodes can actually fail open circuit. When I try to bend the pins, it seems to occasionally make a connection. It seems like the bond wires fail in the diode, or it like mechanically loses the connection to the silicon die, or the pins get loose in the plastic housing. Now the violet diode is in the board, and let's test it. Now it's the right type of buzzing. But now the electrolytic capacitors on the board. It seems like they are in much worse condition than the ones on the front panel. Maybe there is more heat on the board, or it's just a more poor batch. And the rubber seals are cracking horribly, and some of them seem to be leaking already. This one is dirty, and these ones are rusted. White spots here, maybe from leakage. I removed all 10 500 micro 35 volt capacitors from it, and none of them seems completely bad. The ESR is from about 100 to about 160 milliohms in each of them, and their capacitances range from 580 to 720 micro. A bit more than it should be, and ESR is a slightly higher value than a modern good one, but these would still work. But I'm replacing them mostly because they can leak the electrolyte, which can destroy the board. Some of them already leak and corrode, but they still identify as good capacitors. The 100 micro 35 volt capacitor measures 120 micro, this good looking one, and the other identical one measures 160 micro, and this one looks a bit rotten. And the ESR of the good looking one, and the rotten looking one a bit higher. And of course for comparison a modern equivalent, a bit better ESR but not that much. 200 microfarads 15 volts measures 300 and the ESR 117 milliohms, not bad. And the closest modern capacitor is 220 micro, and it seems the old capacitors always measure a bit higher, sometimes significantly higher, but the new ones slightly lower. And ESR comparison, the old 200 micro was 117 milliohms, this one is 36, about 1/3 of it, barely. All the capacitors are replaced. I'm replacing pairs of 500s with 1000 microcapacitors. I don't think the current is so high it would require that many capacitors in parallel, and if they fail I can just replace them again. Now the non-adjustable sections are fully restored and working. I tested everything and it works well. And I'm going back to the adjustable sections and I'm checking it with an oscilloscope to see if there are any oscillations at the output. I have the oscilloscope in AC only mode and the most sensitive setting, but still in time-span mode, where you're much less likely to damage the oscilloscope if something goes wrong. And I'm going back to the adjustment potentiometers, which are on the boards, the adjustable section control boards, and these are some sort of PID regulation or oscillation compensation, basically a negative feedback in the overcurrent and voltage regulation connected to the voltage and current op-amps. And each potentiometer is in a series with a 100 nanocapacitor, a ceramic one, and it has to be set such a way that the power supply doesn't oscillate. Each adjustable section has one potentiometer for the voltage regulation and one for the current limit. Now let's check the output A, adjustable one, and let's turn on the voltage compensation potentiometer. And if it's set wrong, there is some oscillation at the output. Let's go back. It goes back to just the DC, and turning it the other way. And now it oscillates in some other mode, a higher frequency oscillation. So you basically have to find a position where it doesn't oscillate, and you have to recheck it for different voltage settings and current settings and different loads, and find a position where it never oscillates. Well, while looking for the best position of these 4 potentiometers, the power supply just suddenly died. I heard some popping and it went completely dead. Nothing. Not even the indicator lighting up. And the transformer is not buzzing. It's like if the primary fuse blew. And it actually sounded like the popping went from this interference filter, which actually is hot, and it's not heated by these resistors. The resistors are actually cooler than the filter. And of course an interference filter shouldn't be hot, especially when running the power supply with virtually no load. And I was actually told that the interference filters in these are quite problematic, or these filters in general. Here's the marking of the interference filter. It's basically 2 inductors, 1 capacitor live to neutral and 2 capacitors live to ground and neutral to ground. It's a 2.5 amp filter and here's probably what's inside of it. And I guess this 100 nano capacitor live to neutral shorted. This old filter can contain a very problematic paper capacitor, something similar to these disasters. The switch is on, measuring the resistance on the plug and open a circuit. Let's take a look at the fuses. Not sure which one is the primary one. Testing this one, and it's conductive. But wait, the fuse says fast 100 milliamps, but the marking on its fuse holder says fast 2 amps. What the hell? I'm not getting how a fuse unrated by the factor of 20 is not blowing, but let's take a look at the other one. This one is meant to be T, slow 2 amps, and surprisingly it actually is T2 amps, as it should be. And it visually appears blown, and it also measures open circuit. And this is the fuse right at the input. I'm not sure what the other one does. According to the schematic, it seems that the other fuse is only used when you want to use the middle current meter as an external current meter, basically to measure some external current. Otherwise it's completely irrelevant. The purpose of this meter can be switched. You can press this and choose external and use it as a current meter measuring the current through these terminals. Now let's take a look at the filter. And there are also some resistors in series with the primary of the transformer. probably limiting the inrush and also softening the switching of the thyristors in the thyristor pre-regulation. Let's check these resistors, and these are two in parallel, 6.8 ohms, so the total combination resistance should be about half of it, which it is. These were not damaged. And this interference filter has 4 terminals, the ground one and another 4 black ones. I have no idea what is the neutral, what is the live, what is the input, what is the output, but measuring one end, it's shorted to basically everything else. Of course, the DC resistance of these inductors is very low and appears as a short circuit. And when this capacitor is shorted, then any combination of these 4 terminals will show a short circuit. And there are interesting zip ties, which are not zipping in the literal sense. It's actually flat, even, there are no teeth, and it has a ball in it. Instead of zipping, it sort of wedges the ball in between. It looks very similar to modern zip ties, but it actually works a different way. It looks like a modern system at first glance, but it's actually not. So let's not cut it, I like it, let's just slide it out somehow. I just bypassed it for now. And it has a horrible smell of a failing paper capacitor. It actually seems cracked here. Let's give it new fuses, especially the primary one, T2 amps, is important. And let's try to power it. And it seems to run again. And let's go back to the adjustments. The current limit also has a potentiometer for adjustment to prevent it from oscillations. If it's not set right, when you're getting close to the current limit, it will start oscillating, as you can see here. Now the current limit is half an amp, which is in the middle of the scale, and it actually allows it to go over the current limit. But when the potentiometer is adjusted right, the current stops at half an amp and it limits, and there is no oscillation. So these 4 potentiometers are adjusted for both sections, and it all seems to work nicely. And here are the main smoothing capacitors of the adjustable sections. And these capacitors are after the thyristor pre-regulation and before the linear regulator. And the thyristor pre-regulation can reduce the voltage on these capacitors to reduce the losses on the linear regulator, especially when the output voltage is low. Because otherwise the linear regulator would have to drop the full voltage, which can go as high as 45 volts. And this meter is of course measuring on this main capacitor. When I reduce the voltage, the input voltage also is reduced a bit, but it actually reduces even further when I load it. For example, when the output voltage is set to 4 volts, the voltage on the capacitor is just 15 volts. And if I increase the output voltage, the voltage before the linear regulator also increases. Everything's working other than this potentiometer in the current PID regulation in one of the control boards of the adjustable sections is intermittent. Even buckets of contact cleaners are not helping, but I have some new old stock replacements for them. The screw looks slightly different, but otherwise it should be the same. Now the new potentiometer is in. Using a fuse as a current sensing resistor to see the secondary current of the transformer, and of course how horrible the power factor is. Loading it, and this is the secondary current. This goes into the rectification. And now of course the measurement everybody was waiting for during the entire series, the waveforms in the thyristor pre-regulation. The yellow line is obviously a rectified sine wave, and the blue line is the gate of the thyristor. And the thyristor is getting trigger pulses, and when it supplies a lower voltage, the trigger happens significantly after the peak of the sine wave. Here it's happening here. But if I increase the output voltage, the thyristor trigger is advanced, and it happens basically at the top of the sine wave, at the peak. And reducing the output voltage, and the trigger is delayed, and it happens significantly after the peak. Isn't this just bloody amazing? Higher voltage at the output, lower voltage at the output, higher voltage at the output, lower voltage at the output. And turning the current limit down has a similar effect. And the fine adjustment potentiometer I was using a laser printer heater as a test load. It slightly glows at 36 volts and draws about 1.6 amps, but it's intended for 230 volts. And of course everybody was screaming at the monitor that I was testing the interference filter wrong, because in the circuit it was connected to the primary of the transformer. Now actually properly measuring the 100 nano capacitor, and it shows about 0.75 megaohms resistance, which is wrong, and the capacitance of it about 200 nano should be 100 nano, and I guess the capacitor just arced over internally. And ring testing it, 5 rings. Testing it using a lamp in series. Now it started lighting up after about 20 minutes. Nice. That's it. But now let's call it a working power supply. I will find a new interference filter for it, and I will keep using it, and if anything goes wrong, I will make an update. And I decided I will publish a video every Sunday at 14 o'clock of my time, which is noon of Greenwich time, but of course my patrons on Patreon will see the videos several days earlier, so consider becoming my patron. I plan to make regular videos on Sundays and maybe some bonus videos on Fridays. And a big thanks to all of you who already support me on Patreon or using the thanks button.